examples, a case study. This is, I don't know if you guys ever heard of Kareem Abdul-Jabbar, but if you ever were interested in basketball, he was one of the greatest basketball players in the history of the game. Many NBA championships and MVPs. He was amazing. But in his later years, and he was a guy who did aerobics after he retired, kept in very good shape. But in his mid to late 50s, I suppose, he was getting night sweats and hot flashes, and he just didn't feel good. And he went to his doctor and they did a variety of tests, and they looked at his blood, and in his blood, they found a white blood cell count of 200,000 cells per mil versus what's normal is 5,000. So something was wrong. And he was diagnosed with chronic myelogenous leukemia. So they discovered in the fluorescent identification of chromosomes that people that had CML had a very unusual thing. They looked at chromosome 9 and looked at chromosome 22, and you can see the different size and you can see the different colors. And people with CML had part of 9 on 22 and part of 22 on 9. This was discovered in Philadelphia at a cancer institute, and that's why it's called the Philadelphia chromosome. But this is what they call a reciprocal translocation or a fusion gene, where one part of one, when it's multiplying, makes a mistake. And, you know, like I say, it's a bunch of spaghetti, and when it's going to multiply, it has to pull apart. It's a lot of spaghetti, and sometimes a splice goes in the wrong spot, a translocation. And this translocation or chimeric transcripts, sometimes a fusion, and I put a lot of words in here. Exons are the sequences that encode for proteins or amino acids that turn into proteins. So, you know, I talk about 210-KDA. We have a lot of arcane identifications of spots on the gene. Don't ask me how to describe it, but you know, people will talk about ABL gene relating, or BCR relates to a particular sequence that makes a particular protein. Well, everybody with CML had this translocation. Now we know this is what's causing CML, correct? So some really smart guys up in Portland at an academic institution said, well, gee, what is the pathway, the mechanism of action that causes these molecules, the healthy one, what does that look like? And what does the unhealthy one look like? And as you can see in this diagram on the left is the healthy, is the unhealthy stuff, where due to this translocation, ATP or adenine triphosphate, which is again, think of that as a molecule that stores energy, right? Every time you do something, ATP becomes ADP, adenine diphosphate, and releases energy. And when you want to store energy, you take ADP and make it ATP. It's the energy molecule. And this anomaly that happens in translocation allows an ATP to hook up with an enzyme and cause that cancer protein, which is expressed when that translocation happens. Follow?
Yep.
Right. So these guys said, you know what? If we could block or inhibit with a molecule to not allow that ATP to get into that enzyme, then the cancer protein won't be made, and then those people won't be can live with CML. And by the way, we talk about chronic, right? The word chronic in front of a disease, and you probably heard of another term called acute, right? So I want you to know that when we say chronic versus acute, an acute disease is something like I fell and I broke my bone. It happened quickly and it's going to go away quickly. It might kill me, but it's not going to last. A chronic disease pretty much goes slowly, develops over a course of maybe a year and takes a long time. So chronic is a long time, acute is a short time. Okay, so these guys made you see the word Gleevec, but the generic term is imatinib. And let's see what happens. This is called the Kaplan-Meier survival curve. You hear about this all the time. It's a simple thing. You follow a patient in months, and 100% or 1 is everybody's alive on day 0. The probability of survival goes out over time. This was miraculous. By administering Gleevec, patients with CML basically had the same lifespan as a person without this problem. It was a blockbuster, but you got to take it every day. It's for the rest of your life. But from a 30% survival to an 89% survival, it just was incredible. Now, the cool thing about it is we realized we didn't fix the gene, right? The gene was still mutated, but we were able to fix the outcomes or the pathway, to block part of the pathway so it didn't progress into making those proteins that would continue to make those blasts. So we didn't solve the problem from the beginning, we solved it about in the middle. And we didn't allow the cancer, the mutant gene, to do its thing. And that's called an inhibitor, right? We suppressed the upregulation of the proteins that stimulated the blast cells. Complicated, right?